Well, now we're going to discuss a very, very important class of functions, the polynomial functions. And we'll eventually obtain, by the time I get to the end of this board, if I have enough room, that at every point on the real line, x naught, the limit as x goes to x naught of the polynomial is the same value you get if you plug x naught into that polynomial. So you'll see what, if that was unclear, you'll see what it means by the time we get to the end of the board. I'm going to try to use the whole board here, so I won't run out of room down here. I'm going to try to go left to right quite a bit. Well, let's start off with a very, very basic function, a constant function. F of x equaling c, where c is just some fixed real number. We sometimes call this the constant function. If you were to graph it, it's a horizontal line. Well, for this one, if x naught is any real number, then the limit as x approaches x naught of f of x is equal to c. Right? Because f of x is just c. I could replace that right here. I could, actually, let me go ahead and do that. The limit as x approaches x naught of c, well, that's a constant. It's simply the number c. If I wanted to, do I even need to look at a delta epsilon proof of that? Well, it's just one quick line. Maybe I will. The proof let epsilon greater than 0 be given. In this case, we can choose any delta greater than 0. I don't have to say delta equals 1 or 1/2 or 1/10. For any positive number delta, we get the following. If 0 is in between x minus x naught and delta, so what this means is x can just any distance less than delta away from x naught, that implies that f of x minus f of x naught, well, what is that? That's just c minus c. So clearly 0 is less than delta, but no matter what two values of the real line you pick, f of the first minus f of the second is going to give you a 0. So that was quite easy. Now let's take a look at the identity function. F of x equals x for all real numbers. So if you were to graph that, we know what we get. We get that 45-degree angle going through the origin. And f of 5 is 5, f of 10 is 10, f of negative pi is negative pi. Well, if x is anywhere in the real, x naught is any number in the reals, then the limit as x approaches x naught of f of x is equal to what? Well, it's x. All right, how would we prove that? Let epsilon greater than 0 be given. This isn't the only way to prove it, but we could just simply say choose delta equal to epsilon. If we picked any positive number less than epsilon, it would work as well. This is about the worst or best possible case, however you're looking at it. Okay, if we choose delta to be epsilon, then whenever the distance between x and x naught is less than delta, between 0 and delta, we get that f of x minus f of x naught is equal to x minus x naught. And what do we know about x minus x naught? It's less than delta. But delta is equal to epsilon, so I can say, there, that's the end of that proof. Now, I think we've discussed this a little bit before. If instead, and actually it's going to be my next example, if I picked f of x equals, say, 5x, what would we have chosen for our delta? Probably something like epsilon over 5. 5 being the slope. The slope tells us how fast the height changes relative to how fast the x value changes. So let's jump into f of x equals kx. K is just a real number like c was, and maybe I should have just used c. All right, if x naught is a real number, then the limit as x goes to x naught of f of x is equal to what? Well, let me write out, that's the limit as x goes to x naught of, what is f of x? It's a constant k times x. Well, just as I said before, we could use the delta epsilon proof, let epsilon be greater than 0, choose delta to be epsilon over k, and it would look just like this line right above it. Let's see. There's actually a nicer way to do that. Well, maybe not nicer, but we don't have to use the delta epsilon method. This number k can be thought of as a function. Think of it as g of x equals k. It has a limit everywhere. At every x naught, the limit is k, just like this one had the limit of c. So this is a convergent sequence taken by itself. This is a convergent, sorry, not a sequence, but a convergent function, just like this one is, at every real number, x naught. As a matter of fact, we've taken care of both of them. So therefore, the limit as x goes to x naught is going to be whatever the limit of this function is times whatever the limit of that function is. We just discussed that a little bit earlier. So I don't think I'm going to do the proof of that one. But again, the delta epsilon proof would look just like this, only say delta equals epsilon over k. The next one, f of x equals x squared. Well, if x naught is any real number, then the limit as x goes to x naught of f of x is equal to the limit as x goes to x naught of, I'm not going to write it like x squared, I'm going to write it x times x. One convergent function times the other convergent function. Think of this as being this first one, f of x equals x, and this one, g of x equals x. Both of them converge to x. Therefore, this is equal to x squared. I'll go ahead and say by theorem 2.43. Now that's the way I wrote theorem 2.4 out. It may be one off from the way the textbook wrote it, where they only had 3 sections, but I had 4 sections. So the number 3 might be off. And this same thing, right there. Okay, so continuing in this fashion, we know that a constant has a limit, and the limit would be that constant. That's the constant function. We know the degree 1, we know that f of x equals x has a limit. We know that f of x equals a constant times x. We know that a function has, defined as x squared, has a limit as well, and it's x squared. We could continue, and I'm going to say by, I'm not going to do the mathematical induction proof, but I'm just going to say by induction, we can obtain that for every polynomial, and I'm going to write one out, call it p of x, which is a naught plus a1x plus a2x squared plus however high you want to go up to, we're going to go up to n, make this generic. an x to the n. And for every x naught on the real line, I'm just going to state that the limit exists. The limit, as x goes to x naught of p of x, is equal to p of x naught. Just what you get by plugging in that limit point into the polynomial. I got one more thing to squeeze in down at the bottom. But that's highly important. We just showed that every polynomial has a limit at every single point in the real line. And at every point x naught on the real line, the limit happens to be p, the polynomial, evaluated at that point on the x-axis, or x naught. All right, last one. For polynomials, p and q this time, so p of x and q of x, let R1 in squiggly brackets, so it's a set. Let R1, R2, all the way up to Rn be the n roots or zeros of the polynomial q. Be the real zeros or roots or x-intercepts if you graphed it of q of x. Well, let's see. One more line. For all x in the real numbers except for these numbers, we can define the limit of the rational function created by putting p of x on top as the numerator and q of x as the denominator. So we have that the limit as x goes to x naught, I hope you can see that at the very bottom, as x goes to x naught, of p of x over q, p of x naught over q of x, sorry, that would be p of x over q of x. That limit is simply going to be p of x naught over q of x naught. And we're safe now that we only define this to be true for the numbers, this would be x naught, all the real numbers except for the ones that give you a 0 in the denominator. Now, something might be able to be said, and we'll discuss it later. Could the limit exist at these numbers? It's possible. And we'll discuss that later. For the time being, we're going to ignore those and just say the limit of p of x over q of x as x goes to x naught is p of x naught over q of x naught, provided that we're only plugging in for x naught any real number except for the zeros of the polynomial q.